Okay, good day everyone. So what we'll be talking today is singly linked list and their application in Python. So as a recap, okay, again, singly linked list, this is a data structure which comprises of nodes, okay? So it comprises of nodes where each node, okay, would link, okay? There's a single link to its next, okay, to the next item on that list. Okay, so in this case, if we're going to complete this structure, okay, so first is we need to have a node that will serve as our head. So we know that it's our head since we have a location here that states that that is the start of our that is the first node for our list. Okay, and this indicates here the uh, reference for that first node. Okay, now in this example, these nodes here has data 10, 20, and 30 respectively. Okay, so as of now, uh, we still need to supply the necessary references. Okay, so again, if you intend that this node, okay, is the next item for this node in this list is this node here, so we need to supply this reference here. So again, the our node, okay, each node in our linked list is typically comprised of two. Okay, so as a node, it comprises of two parts. We have the data, okay, the 10 here, and we have here the reference to its next node in that list. Okay, so as an object, okay, all of these have their memory location, okay, in our memory. So in this case, we have represented that in this addresses, let's say 1100, 1200, 1300. Again, it doesn't necessarily be consecutive, okay? But to make it easier for you to track which is the next link or what is the reference for that certain node. So I have used this arbitrary numbering system, okay? So if I'm going to write here 1200, okay? So this means that this node, okay, this is the head, okay, this is the first item in our list, singly linked list. So the reference part here would point to the next, okay, the next memory location of the next item or the next node, okay. So in this case, it points to this 200 here, okay. As you get to see, that is their link, okay. Similarly, so we have here, we could write here this memory location. Okay, so we get to say that after this node in the list, it is linked, okay, to this node here where it has a memory location of 1300 and the data of 30. Okay, now let's say this is the last node. Okay, remember when that is the last node of the uh, linked list, okay, the reference would point to a null or a none value. Okay, so let's, okay, since in Python we could represent that in as none. Okay, so we could write, we could use none here. Okay, so now we get to say that this is a linked list which comprises of three nodes where the node, let's say the node with memory location 1100 with data 10 is our first, or which is our head, okay, then followed by this, then finally followed by this, and this will serve as our tail, okay, since the reference points to a none. Now in Python, okay, there is no built-in data structure for this single linked list, but we could still implement this using classes, okay, or object-oriented concepts, okay. So I hope OOP is not entirely new to you, okay, since I believe you already have a subject that you are taking alongside this subject, which is OOP. Okay, so this is like the basics of OOP. Okay, first is, okay, again, as a structure, a singly linked list is comprised of a node, okay, and a collection of node would okay, could refer to a singly linked list. Okay, so let's create here a class of that node. Now in that class, okay, it would, okay, as a template, okay, this would serve as a template. Remember, classes can be used as a form of template whenever we're going to instantiate or create objects for that class. Okay, so we could create. Okay, in Python, we have what we call a constructor method here. Okay, that is required for you to create if you want to make instances of that classes. Okay, so define or def, this is a double underscore, the word init, followed by another double underscore. Okay, then for each for the parameter, okay, of course we have the mandatory self. Okay, then data. Now, we don't really need to, if you notice, diba, not we have data and we also have the reference. But reference, we would set it by a default of none. Okay, so that later on when we're going to add that to a singly linked list, it could be used as part of the head, or it could be used as our tail, or it could be used in between. Okay, so it's much practical this way. Okay, so we have self dot data is equal to data. Okay, so again, I hope I'll not really be discussing the OOP concept behind this, but again, this data and this reference, these are the attributes of this class. Okay, that we get to say that should exist. Okay, for this to be a node, okay, in our singly linked list. Okay, so by default, we have this. Okay, so we can say that by default, okay, our node, let's make this larger. Okay, so our node, every time we're going to create a node, okay, okay, we have this format here. Okay, so by default, we have none as its reference. Then we have some form of data here. So this could be any data, it could be numeric or any type of information that you could store. Okay, as a form in a form of data. Okay, so that's that. Now we also need to create the class for our actual list itself. So we have singly. Again, you could name this any way you want, but please keep it as descriptive as possible. Okay, so we have a singly linked list class. Okay, now as a structure, okay, really, it basically comprises of three types of node. Okay, so we have the head. Okay, we have the nodes in between the. Okay, so we have the head as our first type. Okay, another type would be our tail or end. Okay, which is a reference of none, and all of the in between nodes. Okay, so it is possible that as a list, it could only have one item. So we could say that that is its minimum. Okay, it's a minimum requirement for it to be an existing list. Okay, assuming that there should be data in that list. So we could have, okay, to define, okay, a constructor self. So that's that. Okay, so as a list, okay, really we are particular if there is content, and we know that there is a content in that list if there is a value of our head. So later on we'll see, okay, if this validates it. Okay, if when is it really the case that if there is no head, there's no item in that list. Okay, so that's that. So we have self dot head is equal to none. So as a list, okay, it is possible that, oh no, okay, we have what we call, let's say, as a structure. Okay, by default, we could we could actually store a single linked list with no data. Okay, with no data. itself. Okay, so it's still a valid structure, but it is possible that that is still an empty list. Okay, still it's a valid, it's a valid scenario. Okay, so let us first, let us first create. So let's try and delete this first. Let's try and create this. Okay, how about we're going to recreate this list in our Python. Okay, so could actually do so now. Okay, with this set of classes. Okay, so again, we want to create an instance for this list. Okay, so we could create or we could name that L. Okay, or FLL is equal to singly linked list. Okay, singly linked list. So at this in this line of code would create this structure. So by default, its structure would be like this. Okay, so it would have upon writing this, okay, SLL would have something like this. Okay, so the value of our head is still none. Okay, so this is the initial state of a list of the linked list at this line here. So how are we going to add individual items? Okay, so again, we need to make use of our node class to create these objects. Okay, so what you can do is you could write, so let's say we have n1 for our first node. Okay, technically this would serve as our head. Okay, so I want this n1 to be an object representing this data here. Okay, of course, this would not really be the case. These are just arbitrary locations in our memory. Okay, so it could only be determined during program runtime. Okay, so let's say n1 is equal to node 10. So at this point, okay, so at this point, okay, it would create an instance of this class here. Okay, so remember, when you're going to make use of this, if you're going to instantiate, okay, an object under that class, okay, you might as well disregard the self parameter, okay, upon actual usage. So we could say that this is the this data here or this 10 here would supplement this parameter here. Okay, so we could have a node. Okay, let me move this. Okay, let's do it like this. So, now, okay, so that is none. So we create a node here. Now at this point, it is still not really, it does not really still associated with a node in a singly linked list. So it's like a floating, floating object, okay, in our memory. Okay, so we have here. So let's say, okay, assuming it would create this memory location. Okay, so let's say nah. Okay, again, this is arbitrary. Okay, siguro we could print this. So print and want to see really that there is a memory allocation for this object. So if we're going to run this, as you can see here, okay, so here, there is an object at this memory location. Okay, so I think every time we're going to run this, it would create another location. Okay, so again, you'll notice it's another different location. So really, we could not really set a fixed thing here, but at least we could represent an arbitrary number to represent that specific location. Okay, for that node. Okay, so na. Now, how are we going to make this our first, okay, first node in this linked list? Okay, so let me supply the data portion here. Let's say that. Okay, we simply, okay, we simply assign the value of our head. Okay, the head of that linked list, single linked list to this reference here. Okay, so remember data, reference or link to the next node that it should point, okay, or the next item. Then this is its reference as an object. Okay, so we simply are going, we are going simply to assign the value of our head. Okay, so this we are going to provide the value of that with that. Okay, now what we can do is we could simply write, okay, SLL dot head. So we are accessing, okay, we are accessing this attribute of our singly linked list. Okay, remember we have created this. Okay, so we have created SLL as an instantiation, okay, or as an instance of this class here. Okay, so we could then use this. Its default property as of now is none, but we are going to update that. So we're going to change that to N1. Okay, so now this would become, okay, it would store the reference. Okay, okay, so it's going to store the reference of this node here. So we could have 1, 1, and that. Okay, so how about we're going to add another node? So let's say this node here. Okay, so again, we're going to create another node by instantiating another object under this class. Okay, so whenever we're going to instantiate, we need to supply this data here. Okay, so let's say 20. Okay, so now after Python would interpret this, it would have a node that would be created having this information. Okay, so we have the data 20. Okay, then as of now, it still points to, or the reference is none. Okay, also the reference here, okay, actually it's still none. Okay, wala pa, we still haven't pointed this to this node here. Okay, so to go back, okay, ano ya, you might have been confused since I have actually forgotten to state that this is still none. Okay, so let's go back. Let's go back. Okay, so after we created this, okay, we are going to add a node. So before we get to add a node, we still need to create that actual object, okay, or an instance for this class here that we are going to save as an object in our program. Okay, so we create a new object, okay, by writing this statement here. Okay, so node 10, you are creating a new instance of this class, okay, provided that the data is 10. Okay, so this is what happened here. Okay, so in this line of code, it generated this part here. So let's say this is still none. Okay, diba? As I mentioned earlier, upon creating this, the value of our head is none. Okay, I think you get the idea here. Okay, so at this point, there's still no link. Okay, there's still no link for these nodes that I have indicated here, or in this case, these two. Really, this is not a node, but this is just a pointer. Okay, this is just a pointer that holds the value of our head. Okay, but at this point, the value of our head still is none. Okay, so at this line, this is the object. Okay, that has supposedly been created. Okay, so at this line, so this is the object that has been supposedly created. Now, at this line here, okay, we assign the value of our head to this object here. So we essentially point, okay? So we could add an object here, let's say shape, okay? So we could point like that, okay, to give emphasis. So this is our head. So how are we going to do that? So we assign the value, we're going to assign that object to this uh, property here, attribute of our head of that singly linked list. So that would be represented by the memory location here. So next is we want to add another another node. So we can say that this is already a valid list because it's possible that as a list it could contain one item. Okay, so the one item serves as the head, and also since it points to none, okay, its reference is none, it also serves as the last item. So we could say that this is the first and last item in that list. But let's say we want to add another item here. Okay, so we're going to instantiate another, okay, object or another instance of this class. Let's say node, say we're going to add here 20. So at this point, okay, this object has been created. So let's say its memory location upon creation of this object is 1200. Okay. Now, the data is 20. Now, how are we going to link this? Okay, how are we going to how are we going to create a singly linked list where the items, the first item is this, then the next item is this node here. Okay, so again, by default, that is none. Now, what we can do is we change the reference of our head here to be pointing at the reference to the next node that is supposedly the next item in that list. So in this case, it's N2. Okay, so we could either, or we could write it like this, N1, okay, dot head, okay. Remember, not head, okay, it should be a reference, okay. So, so N1 dot reference, okay, so we're going to change this, okay, so this is our N1 reference, okay, the reference of that would be equal to the memory location, okay, the memory location of this object here, which is represented arbitrarily by this 1200 value, okay, so we could simply call the object itself, okay, so N2, okay, so now instead of none, it is now 1200. Okay, so graphically, we could then say that this is linked. Okay, so copy this. Okay, so this is now linked to this by these values here. So now we have this last item. So let's say we're going to add another. Okay, so again, we simply need to create another node here. Okay, so node, let's say 30. We want the data to be 30. Okay, so it would create this object here. Again, an arbitrary number, let's say 10,300. Okay, then we have the data 30, then our reference is none. So similarly, in what we did earlier, we want to make this as a collection. We want to point. Okay, we want to point the next item after this node here to be this node here. Okay, so again, we are going to change the value of our N2 reference. Okay, so this part here. So N2 dot reference or dot ref is equal to what? Okay, this node here. So we have N3. So again, graphically, we could say that that is linked there. So now we have a singly linked list with three items, okay, having this node as the head or the start of our list, okay, this as our last item since it has a none. Oh no, we still need to change this like that, okay, since the moment that we did this, okay, it would change the reference of this value here, of this reference part here of node 2 to be pointing to this node here, which is that value. Okay, so you get to see this points to this points to that, this points to that, and this is our last item since it does not point to anything. Okay, now how are we going to verify if this really exists? Okay, how could we display this structure? Okay, so what we can do is we could create, okay, we could create different, later on we're going to create different methods under this singly linked list class that we could use to add, okay, and traverse, okay, and delete, okay. So siguro we'll limit with with those options, with those methods, okay. We're going to traverse in order for us to display, okay. Then we also need to insert, okay. Then we also need to delete, okay. So first is we want to see or to check if this would really create a singly linked list structure. So def init, okay, since this is just a method that would be, or it's an action that is being performed. So it's that it doesn't really receive any uh, parameter. Okay. Now, the contents of a linked list, okay, there are actually two states, okay, if there is no content or if it's empty, or if it's not empty, okay. How do we know if the list is empty or not? Okay, remember when we initially create a linked list, okay, it's actually empty, okay. We know that since the value of our head is none. So when we say that the value of our head is none, it means that though there is that object, okay, there is an object for a single linked list that has been created, but the list themselves or the node themselves are still not present, okay, in that list. So we can say that if self that head is equal to none, then we can say that the list is empty. Okay, so list is empty. Else, if it's not none, meaning there is a value, okay, in this case, in our structure here, the value of our head, there exists a reference there of our first node. So it's not empty, it's not none. So else, okay, what we're going to do is we're essentially going to traverse, okay. So this is the traversal, okay, of all items in our list, okay. What we're going to do is we keep a temporary variable to check, okay, to check the values of our memory location, or the node's memory location, and the node's reference, okay. What we're going to do is first we check the head, okay. If there's a value of head, okay, then supposedly there's a node that points to that reference, okay. So this points to here. Now, if that is the case, we want to display the data part, di ba? We want to essentially display the values 10, 20, and 30. Okay? It doesn't make sense to display the values uh, for our memory location and our references, since that is just it's quite uh, a complicated number which changes every time. But practically speaking, we are concerned with the data that we are going to display. Okay, so what we're going to do is check if there is a content here, then we go to that reference. We go to that reference. Okay, we're going to check, okay, the data on that reference. Then next is we're going to check where it points to. Okay, actually it's just a loop. Okay, you'll notice. Okay, check. This is a reference that is pointing here. Get the data. Check the reference. Okay, get the memory location. Get the data. Check the reference. Get the memory location. Check the data, and check the reference. Now, we are going to do that, okay, until the value of our reference is none. Okay? Now, we could actually do that by constantly updating a single temporary variable. Okay? So let's say we are going to name that variable n. Okay? So, what is the first thing we need to do? We are going to check what is the value of our head. Now, since if it's not none, or if it's none, we're going to print empty. But if it's not none, then it should point to another node. Okay, if it's not none. Okay, so n is equal to self dot head. So essentially, we are just starting with our traversal. Now, while n is not equal to none. Okay, while it is not none, we're going to print the data of that node. Okay, so we could say that n here would be is representing the node that we are currently working on with. Okay, so during our traversal, this is the node that we are referring to. Okay, so in that node, okay, and self.head. Okay, while n is not none, since at this point, okay, it's not none. It has a reference to 1100. Okay, so it moves here. Okay, now we could actually print, okay, and that data. So at this point, the node is represented by this object here, okay, or this variable here, n, okay. So n that data at this iteration is this value of 10 here, diba? Okay. So you can say to emulate, okay, to emulate this part here that it points to a next node, we could change or we could add here an arrow pointing, okay. So what it would actually print, okay, this, okay, this and this part of our linked list, the data and the arrow, okay. It's not really required to it's not really required to print the arrow, but it helps visualize the structure of the linked list. Okay, then we could change and here instead of uh, moving to a new line for every print statement. Okay, we are going to write space. Okay, I think you already know what that means. Okay, so after we have printed the data, we need to check on this what is the content here. So remember, this is the reference of that node. Okay, so this is the part here. Okay, so data is this part of our node. Then reference. Okay, we need to check on that reference to see if where it points to. Okay, so how do we let it? How do we? Okay, how do we pick? Okay, essentially we are picking. Okay, we are checking if there is a value. Okay, so we could simply, okay, after printing that data, we could write, okay, and we update the value of our n to n dot ref. Okay, so again at this point, okay, it checks for the head. Okay, so if it's going to point, okay, here. Okay, it technically points to this node here. Okay, while n is not none, since 1100, okay, take note this is the value of our head. At this point, n would hold the value of our self.head, okay, which is this value here, which points to this reference here. Since it's not none, there exists a value for that, okay. So we are going to do this thing here, okay. So this is a loop. We know when to stop. We stop when n is none, okay. So let's say n dot data is this part here of our node. Okay, so again, this is just visual representation. Then we are going to reassign the value of n to n.rep. Okay, so what this will do is n.rep is this portion here in our node. Okay, this would then be used to check if this is none. So you get the idea. So n.ref at this point here, okay, and this example is 1200. Now, since 1200 is not null, okay, so at this point, it is now pointing to this location here, okay. So, the value of n here, let's say, is some value, let's say 1200, okay. Since it's not equal to none, it's going to perform this step. Okay, so it accesses this data, then it reassigns the value of n to the reference here. Okay, so at this point, we have 1300. Okay, so since 1300 is not none, okay, or the reference is not none, really, after the first iteration, n would refer to the reference of the node. Okay, so if the reference is not none, it's going to print this here. Now, since the value for reference here is 1300, so it's actually accessing this node here. Okay, so you get the idea. So it's going to print, okay, and that data, then it reassigns the value of n to n.ref on that current node. Okay. Now, since the node here, okay, upon checking, okay, since n here would be and the n dot reference here, the value now would be equal to none upon traversing to this part here, essentially the last item of our list. Okay, it would this would no longer be true, then it would stop iterating. Okay, so ultimately it has traversed through the entire part of our list. So to check, okay, we simply would call, okay, this method. So SLL dot uh, we still haven't yeah, we still haven't named this. Okay, it's not really in it. Sorry for that. This should not be in it, but this should be display. Okay, so init really is a constructor method. Okay, it's just one method. There should only be one. There's usually one init method that is used as a constructor whenever you're going to create an instance of this object. Okay, so other methods typically would include the other things that we could associate for this object, okay, or this class. Okay, so sorry for that. This should be define the name of our method that we're going to call when we want to, let's say, display this data. Okay, so you could simply write display. So if we're going to run this, okay, we can see. So we have this. Okay, let us show the code. Okay, so you can see here that there really is a structure, a single linked list that has been created with the data 10, 20, and 30. Okay, so that is how you're going to display your data. Okay, so if you're going to add, okay, let's say we want to add a fourth, okay, fourth item. Okay, later on we're going to create methods that would do the actual adding. What we are doing in this case is we are actually manually, okay, uh, we're manually adding items or nodes in our singly linked list. But later on, we're going to create a method that would do the actual adding and linking, okay, to these nodes in our list. Okay. So let's say N4 is our fourth node. Okay, we're going to create an instance of this class with the data, let's say 40. Okay, then we are going, di ba? Since this is still, okay, this is still floating, okay? So what happened here is, okay, let's say we create, di ba? Remember how the process is being done? All borders, okay? Upon doing this would have this node here. Still, it's still not linked, but we will going to link that, okay? So how are we going to link that? So what is this node here? That is N3 dot. So what is this part of our node here? That is the reference that would point to this node here. Okay. So let's say it has an arbitrary value of 1,400. Okay. So we want to put 1,400 here. Okay. We could do that by writing N3.ref is equal to N4. So now it is supposedly linked to this part here. So if we're going to run this, we could see, okay, that there is the fourth item here. So this, we could say that this points to none, okay? So this points to this. So this node points to this node, then this node points to none, indicating that this is our last node, okay? So quite straightforward. So next, how are we going to, okay, do this programmatically, okay, or insertion? So let's say this is our display, printing, printing of elements, or we could say nodes, okay, printing of nodes. So how are we going to create, okay, or how are we going to perform insertion, okay? Now, there are usually three insertion methods, okay? We insert or we add, okay? Insertion or adding, okay? We add from this start, okay? So we add, diba? So we could add here, okay? We could add here, we could create, okay? Okay, so we could create a new node that would be situated here, okay? So what would happen is this would become our second node, okay? So this would become our second node if we are going to insert a node at the start. Or another usual case is we are going to add a node at the end. So meaning the original end here would become our second to the last. Okay, I think we have already discussed this. Okay, how are we going to make a node? Okay, how are we going to make a node? That node to be the first node in that list. So we could simply assign the value of that reference, okay, to our head here. Okay, so let's say if we are going to, let me, can I move this? I think I can move this. Okay. So what we're going to do is we're going to, let me erase this since so that it will be less cluttered. Okay. So what I want to do is, okay, I would like to create, okay, a node, okay, a node that is supposedly our first item here. Okay. So what the how we're going to do this really is ngani. Okay. So whenever we're going to create a new node, let's say this is 1,500. Again, the values here is not really mean anything. Okay. Aside from the fact that this serves as the links between the nodes. Okay. So let's say we do created this node, okay, later than the rest, but we want to add this at the start. So how are we going to do that? So first is every time we are going to create a new node in that list, okay, we are really going to create or we are really going to instantiate, okay, create an instance of that class, okay. So essentially, we are creating an object for that class, okay. So whenever we're going to create a node, okay, what it will do is, okay, assign a memory location for that node. Then it would ask for the data. So let's say I'm going to add 50 here. Okay. So few things in mind that you need to consider. Okay. The value of head, if you want that the node, the first element or the first node of that list would be this node, we are going to change the head value here. Okay. So in this case, let's say the head value should be 1,500. So it should be pointing. So if I can move this, okay, na. So it should be pointing there. Okay. Now the reference. Okay. So that is these are the things that you need to consider. The value of our head now should be pointing to the newly created node, and the reference of that newly created node should be the reference of our original head, which is this 1,100 here. Okay, so we're going to visually represent that in this manner. Okay, so that is adding, okay, at the start. So let's work on that. So let's say inserting or insertion or adding. Okay, we're going to define a new method. So let's say add beginning. Okay, so since we know where to add that, okay, it would be the beginning, okay? So really we're just concerned with the data, okay? So self, then the data, okay? So we're only going to ask that. So, we are going to only ask, okay, for the data, okay? So first step is we're going to create a new node. So let's undo this first, okay? Like this, okay? So we're going to create a new node, okay, by writing, okay, essentially doing it like this, but in a more programmatic manner, okay, a more dynamic manner. So we have new node is equal to, what we're going to write, node, okay, then data. So whatever data that we provided here, whenever we're going to call, so how are we going to call that? Okay, let's say we're going to write. Okay, we're going to call this method here. Okay, so you can say s uh, sll dot add beginning. Okay, so let's say we're going to add at the start of our list the data 50. Okay, so this 50 here will be supplied. Okay, whenever we're going to create this object to this part here. Okay, so new node would be equal to this instantiation of this class here. Okay, so the data would be this value here, 50. Okay, so actually similar to this, to what we have done here. But again, this we manually did this. Okay, so next, we are going. Okay, so now we have, so at this point, uh, assuming that we have finished, okay, the definition, and we have called this, okay, so this would be, so let's say, some 1,500, okay. Again, this is an arbitrary value. This is being determined upon creation of this object. Okay, so this is a memory location. So, kana. So 1,500, we have the data of 50. Then, remember, whenever we're going to create a node, okay, the default value of our reference is none. Okay, so next, we're going to assign the value of our reference for that node. Okay, new node dot reference is equal to, what do you think? Okay, at this point, di ba, you've noticed the value of our head is still pointing to this node here. So where could we access the reference to this? Okay, where could we access the reference to this node, which would ultimately become the second item in our node? Okay, gusto na to, or we would like to access the memory location of this node here. Now we could actually access that by calling the head. As you can see here, this is the reference to this. Okay, so new node dot reference is equal to self dot head. Okay, so whatever the value of our head here would be used to would be used as a reference to this here. Essentially, we are making this, or we are going to add a reference here to this node here. So upon this step, okay, so we're going to update this. Let's say this would become, what is the value of our head? That is, at this, let's say in this example, we have 1,100. So 1,100. So we can say that at this point, this has been linked here. So is this enough? Not yet. We still have to update the value of our head, that it should be pointing to this reference or the memory location of this new node here. So we can do that by changing the value of our head to the reference of to the memory location of this node here. Okay? And so how are we going to do that? We'll simply going to write, okay, self dot head is equal to what? New node. Okay, similar to this part here. Okay, so we have called for the memory location of that node to be our new head. So with this, okay, at this point in our program, this is now, okay, this is now pointing to Ana. So now we have a new node that we have added at the start of our list. So if we're going to do this, okay, we expect that this 50 would be the start, the data of our first node that we're going to display, or we're going to see when we are calling this display function here. Okay, so if we're going to run this, as you can see, 50, okay, so 50 is being added at the beginning. Okay. So what happened here is it created this list first since this has been created before prior to this add beginning method. Okay. It created this. We manually or we hard codedly created the list, single linked list. So this point here 10, 20, 30, 40. Then upon calling this method here, okay, we added the data 50 at the beginning. Okay, as you get to see here, originally this is our head, but now that is the second element or the second node of our linked list. 50 is our new head. Okay, so that is adding at the beginning. So how about adding at the end? Okay, so let us remove first our fourth. Okay, so let us limit so that the image that you get to see at the right portion is not too small. Okay, so let's delete. Okay, so if we're going to run this, we should okay. Now we're going to run this as you can see here. Okay, okay. So we are working on this list. So what I want to do next is I'm going to add, let's say 60. Okay, I'm going to add the data 60 at the last part. So after our 30. So originally or prior to that, we have the tail. Okay, or we have the end. Okay, with the data 30. But we want that when we're going to add a new node, it would be situated at the last portion. Okay, so how are we going to do that? Okay, so what we can do, again, there are two scenarios. Okay, so the first step really is to create a new node. Okay, after that, we're going to check if the value of our head. Again, there are two states that a singly linked list could exist. It could be either empty or not. So if it's empty, then we would technically just assign the new node to our head. So, di ba, let's say uh, we still have no items. Okay, so let's say we still don't have no items in our list. Okay, so upon creation of our single linked list, so let's say we created SLL. Okay, so SLL. Okay, let's say this portion here would be our okay. This portion here would be our okay. So creating SLL like this is creating, let's say, a memory location, okay, with initially with no contents at first, okay. So there are two states, either that single linked list is empty, as is in this case, or it is not empty. Let me, okay. So it's possible that it's not empty. So let's say uh, we represent that as like that, okay. So this is the possible states of a single linked list, okay. So it could be mm, okay. Mm, no border. Okay, so there's two possible states if there are items, okay, or if it's empty, okay. So if this is the case, okay, when you're going to add at the end, okay, okay, for, if you're going to add, actually this is also true when you're going to add at the beginning, okay. So if we go back, Okay, if we go back to adding at the beginning, di ba? Add at the beginning 50. Okay, so we created a new, let's have a variable here or a pointer here for our head. Okay, di ba? When we're going to create, okay, whenever we're going to create a single linked list, okay, initially it would create this structure here. Okay, so it doesn't have any contents. All it has is a head value, okay, that is set to none. Okay, it has a head pointer that is set to none. So if we want to add, okay, if we are going to add at the beginning, okay, regardless if it's empty or not, we are just actually pointing, a reference to our head. So going back, if we are going to do this, okay, SLL.add beginning 50, okay, so upon calling that method, we are going to create a new node, okay, so with the data 50, okay, let's change that to 40. Okay, 40. So we are going to, let's insert. Okay, so we're just creating, okay, a node here. Okay, at this point, okay, new node. Okay, data node 50. Okay, so we have the data here. Then we have none here. Diba? Again, I've already told you why it's none. Since every time we're going to create a new node, okay, this would be its default, okay, attributes, okay, the data that you have passed here and the reference, okay, which is this part here, would be equal to none. So regardless if it's empty or not, okay, really what you're doing is you're just giving a new value of our head, okay, the new reference, okay, or the new value of our head that points to a reference to the supposed first node, okay. So we would simply, diba? So new node, then new node dot reference is self dot head, okay. So the value of our head, uh, so new node is equals to node dot data, okay. New node dot reference, okay, is equal to no, okay. We still need, sorry, we still need to create a method if our list is initially empty. Okay, if we're going to retain, okay, if you're going to, diba, new node, okay, here, new node that reference is self dot head. The value of our self dot head really is none, okay. Well, let's see. Forget to continue. Self dot, okay, sorry. Okay, it's okay pala. Okay, new node is equal to no data. Okay, new node dot reference is equal self dot head, okay, which is none. At this point, self dot head, I happen to update, okay, when we're going to assign the reference of our new node, okay. I was confused since I really didn't add, let's say, uh, so 1,500 here, okay. So the self dot head would be new node, the reference of the new node. So at this point, okay, regardless if it's empty or not, or in this case, it's empty. So we have 1,500 here. Okay, so we have, so again, okay, sorry if it was confusing, but really, regardless if your linked list is empty or not, adding at the beginning, okay, calling this method would work as is. Okay, okay, or let's say this is another linked list. Let's say this is 1,600. So of course, the value of our head here is nana. Okay, how about adding at the end? Okay, now adding at the end, okay, if it's empty, okay, it's essentially calling adding at the beginning. Okay, so let us write that first. So def add end. Okay, so again, what we're going to need self then data. That's na. Okay, so new node. Okay, first step, we're going to create a new node, diba? Every time we're going to add, we are actually creating a new object for that node. So, na. So we're just going to replicate, or we're going to create the equivalent code that has transpired earlier. So node is equal to data. Okay. So if it's empty, if self dot head is equal to none, we are just essentially, okay, doing something like this. Self dot head is equal to new node. Okay, as simple as that. Okay, else. Okay, so what we did really is we just perform this part in our uh, add beginning. Okay, it doesn't really replicate the actual. Okay, so really what it did is it actually if you're going to see, it did replicate this, diba? So new node is this, diba? This is the step here, then, diba? So if self.head is equal to none, if it's empty, so self.head, okay, so not really the same, but I hope you get the idea, okay? If it's empty, or if it's, yes, if it's empty, so if self.head is equal to none, indicating that there is still no items or no nodes in that list, so we assign the value of our self.head to that new node. Else, ngani, okay? So again, we're going to do similar to this, okay? In which we are going to check if something is none, okay? Now, really, what we want to check is as long as the node that we are traversing, okay, until we encounter, okay, until we encounter, not as long as, until we encounter that the reference is none, then it would base the adding of the node by this iteration here, or by this iteration. Okay, so let's just code this. Okay, then we're going to uh, emulate this. Okay, so n is equal to self.head. Again, if head is not none, meaning let's say in this case, uh, we'll work on this uh, supposed linked list. Okay, so this is a linked list with one item. We want to add a new item here. Let's say 60. Okay, so and we're going to assign a new variable or new object. Okay, so anyway a container of our head. Okay, so initially, so self.head while n dot ref. Okay, so what is n dot ref? So n at this point is self.head. Okay, so the value of our head is really this 1600. So this memory location here. Okay, what is n dot ref of this memory location? That is actually this portion here. Okay, while it is not none. Okay, so while it is not none, it would continue to traverse. Okay, so let's say, let's make this none. Okay, so let's say the value of our head. So let's see, let's work on this example instead since we already have nodes in this list. Okay, so n is equal to self.head. Okay, so essentially it points here. Again, this is a pointer, ha. Uh, it might be misleading. You might be misled that this is a node, but really this is just a pointer. Okay, so it's just a pointer which indicates the head. So the actual nodes themselves are these things here. Okay, kane, 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 kane. So when I say n is self.head, really it looks for the value of our reference that is being pointed by the head, okay, which is this node here. So essentially, this part here is pointing to this location here. Okay, so n dot ref really is this. Okay, remember this is n. Okay, self dot head. So this is this part here. Okay, n dot ref. Okay, it's like writing it as self dot head dot ref. Okay, but at this point, so n dot ref here is actually this part here. So if it's not none, meaning if it's still not the last node in that list, we are going to traverse. Okay, we want that we arrive here. Okay, but remember the disadvantage of a linked list. We are traversal really is to the big O of n, di ba? It depends on the size of our input. Okay, so really yeah, the worst case possible is we traverse to the entirety of our list. Okay? So, again, going back, as long as it is not null, we are going to traverse. So how we do that? We are just simply updating the value of n here is equal to n dot reference. Okay? So, this n here would be used, okay, as the basis for this loop to continue. Okay? So, at the initial iteration, it would start at the head. The rest, it would refer to the current value of the reference on that iteration. Okay? So first, again, first iteration, it points to here. Okay? While n.ref is none. N.ref really is this 1,100 here. It's not none, di ba? There's a value there. So, n is equal to n.ref. So what is n.ref? That is 1,100. So it now points to here. Okay? So ihanap na i-check. Okay? Is n.ref at this point is equal to none? Since that is false, okay, it would assign the value n or n.ref to the value to the variable n. Okay? So what is n.ref at this point here? It's 1,200. Okay? It's going to check. Is n.ref, okay, none? This point, delete. No. Okay? It still have a value of 1,300. So it assigns this value here to this variable here. That it gets to iterate again. Now, at this point, upon checking n.ref here is none. Okay? So n.ref is none. Now, what we want is we're going to stop there. Okay? So we now have the reference, okay, of that node of the last node. Okay? So we now know that that node is the last. Okay, since the value of none is the value of reference is none. So upon that, okay, we are going to essentially write, okay, essentially point, okay, di ba? Remember we want to add, okay? So let's work on this linked list na lang, okay? Remember we want to add, so let us move this, ano, let's just insert. Okay, I think it's still large enough for you to see. Let me change na lang this. Okay. So if it's none, okay, the node that we have created, okay, so if we continue, and that ref, the new value, okay, okay, and reference are the new value of that reference would be, diba? Essentially, we are the purpose that we are going to this last point here is we're going to add a new node. Okay, okay. So upon arriving at this point of our linked list, which is the last node, okay, we want to point the reference of that new node. We want to update this to be pointing to our new node. Okay, so let's say we're going to now. Okay, let's say we have a new node. So we want that this would be pointing. Okay, this would be pointing here. Diba? So essentially, this is no longer none. Okay, so the address, the reference here would points to the reference of our new node here. Okay, so let's say 1600. Okay, then let's say the data. Okay, assuming that we have created the new node. So let's say we add the 40. Okay, so 40, then none. So we want to change this, di ba? Remember, this is our original last node in our list. So we want to change that to 1600. So how are we going to do that? And that ref, di ba? We have stopped here. We have iterated tamandare. Okay. At that point, we still haven't linked. Okay. Don't worry, we will be emulating that. Okay, once we are done with our code. Okay, but really we want to update. What I'm trying to say here is we want to update the original and uh, the original end node of that list to be pointing to the new node that you want to add at the end. Okay, so nref is equals to new node. Okay, and I think that's it. Let's try. Okay, so again we're going to delete this. Let's just delete. Oops. Ano. Okay, so we want, okay, so we want, let's say, ano yun? So SLL dot add end. Okay, I want to add, uh, let's say 50. Okay, so let's say I am trying to restructure. I'm trying to modify this. Okay, let's say ano lang nga. Let's just run this. Siguro you have already forgotten how this looks like. Okay, we're going to run this. Okay, we have 40, 10, 20, and 30. Okay, in that order. Okay, so 40, 10, 20, and 30. So we want to add 50. Okay, essentially we want to do something like this. Add and then 50. So gusto nato mabutang og, okay, okay. We want to add a new node here that would hold the value of 50. Okay, we want to add it at the last. So how are we going to do that? Okay, so add n 50, you call that method. Okay, so SLL dot add n. So that's the thing here. Okay, so first thing, new node. Okay, so again, we're going to create our new node. Okay, upon creating that node, so let's say we have 1,600. Let's check if there's no redundancy. Okay, so we have 1,600. At this point, we have the node that we are working on had the data here, which is probably written here 50. Okay, so at this point, so this is 50, this is none. Diba? Whenever we're going to create a node, it would be like this. Whatever data that we have provided, okay, internally, memory location would be assigned. Then we have the reference of none. Okay. Now, since this is false, okay, diba? This is not empty. Okay. The list that we are working on is not empty. Okay. So it's not empty. There are existing lists. So we proceed to this part here. Okay. So what we did here really is we are just traversing. Okay, we want to go to this point here. So n is equals to self.head. So it now points to whatever it should have been. Okay, so whatever reference is pointed at the head, which is whatever node that has a reference pointed by the head. So this part here. Okay, n is equals to self.head. Okay, so that's our current pointer location. Okay, while n.ref is not equal to none. N.ref is this part here. Since it's not equal to none, there's a value there, 1100. We're going to reassign the value of n to n.ref. Okay, so n is equal to n.ref. So the new value of n here, okay, instead of 1500, it's now 1100. Okay, so since 1100 is not equal to none, okay, tama ba? Okay, sakto. Okay, so when it's not equal to none, so n dot ref is not equal to none, di ba? It's 1,200. So we are going to use n here would be n dot ref, which is 1,200. Okay, so it now points to this part here. N dot ref, okay, n dot ref, okay, or the value of n here is, okay, what is n dot ref? Okay, this is n, this is n dot ref. Okay, so this is n, this is n dot ref. N dot ref is not still not none. It's going to, okay, assign the value of that to n here. So unsay value sa tong n? That is n dot ref, which is 1,300. So now it points to this node here. So what is n dot ref of 1,300? Okay, since it's 1,600 and it's still not none, okay, it's going to assign the value of n dot ref to n. Okay, so n dot ref is 1,600. Okay, so that is the value of n. While that's the value of n now. Okay, n dot ref is none. Oh no, really, we we actually haven't changed this. Sorry. Okay, I haven't fully resetted it. Okay, so it should have supposedly end here. Okay, since mao ni ato ang bag-o nga node nga gihimo. Okay, kanila. Okay, going back. Okay, so n is up that head points to here, n dot ref points to here. It's not none, so n is equal to n dot ref. Okay, n dot ref is 1,100. So is n dot ref none? So n dot ref here at this iteration is 1,200. It's not none. So it continues to do that until, okay, upon checking if n dot ref, okay, upon checking here, if n dot ref, okay, is, if n dot ref here is equal to none, okay, since it's true, Then, okay, we stop iterating. So we stop here. So the value of n would currently point to 1,300. Okay, so n here would be 1,300. Did you get the idea? It traverses from start and until the original, okay, or the last node, okay, the last node of that list. Okay, it stopped when upon checking this. Okay, so upon checking that it's none, okay, it stops. So the pointer or the iteration actually ends here, where the value of n is 1,300. So you can say that in this example, okay, n here is 1,300. So 1,300, okay, dot ref. So this is the the reference of this node here. We are going to change that, di ba? We are assigning the new value of that to the new node. Okay, essentially we are assigning the memory location, okay, to be pointing, okay, to this new node. Okay, so assuming that the value of the reference of our new node is 1,600, okay, yung memory location is 1,600, we are going to use that value to assign that here. So this is what happened here. So and that ref, the new value of that is new node. Okay, so now have this part here. So with this, we could visually say, or we could visually represent that, okay, it's now pointing to that. And we now know that this is the end of our list. Okay, di ba? The method ends here. Okay, since it's already enough that we reassign the value of, we change the value of our non of our original end of our node here to the new, okay, node, the memory location of our new node. So if we're going to run this, okay, so we should see, okay, 40, okay, so 10, 20, 30, then add beginning 40, so 40, 10, 20, 30, then add end 50, okay. If we're going to run this, as you get to see, that is the case, okay. So this has been created manually, calling, so Tanisha, this is the point here, this line, add beginning, it resulted to this, okay, then finally add end, it resulted to this, okay. So next is adding in between or after, okay, after a known. Okay, so let's say, mhm, so we have managed to create methods that would add, okay, add at the beginning, add at the end. Now how about adding in between? Okay, there are actually two scenarios that you could add in between. Either you could add after a specified node, okay? So let's say if you specify that this is your node, then adding a new node after that, what would happen is something like this, okay? Okay, So let's say after this node, okay? So adding in between, there could be two scenarios. You could add after the specified node or before the specified node. So if after, what would happen really is something like this. So again, we create a new node. Okay, so let's have it done like this. Okay, oops. Okay, so let's say a new when we created a new node. Okay, when we created a new node, what we want is this would be situated. Okay, if you say after this node, what would happen is the newly created node would be situated between this, okay, the node that you have specified in between this node. Okay, so you're like inserting this here, di ba? So let's say this has a memory location of 1700. Okay, so new data is the data is, let's say, 60. So what you want to happen is let's insert. So you want that this, okay, let me use a better, I think this would do. Okay, so let's say you want this to be pointing here. Let me find illustration. So this would be enough. Okay, so what you would like to do is this would now be pointing here. Okay, then this would be pointing here, diba? So you get the idea. So this would be pointing here, and this would, of course, okay, would not be linked there, diba? So it's like inserting this here. So what you would like is, instead of the reference of this node that you have specified to be 1300, which was originally the case, you want that to be 1700, okay? Then this, the newly created node that you have created, okay, that you have decided to add in between or after this node here, it would point to Ngana. Okay, so this this is when you want to add a node. You want to add the node after the specified node that you have indicated here. Now, it's also possible that, let's say, you want to uh, add before. Okay, so you want to add before. So if you say add after this node here, so you created, okay, you are creating a new node that is in between the original next node of this. Okay, so you have inserted that here. Okay, I hope you could visualize. If you say before, then you could say that, okay, if you're going to revise this, okay, so let's say this is originally 1300, diba? If you want to say before, so you want na it would be indicated here. Okay, so before 1200, you want to add that node. Okay, so what would happen is, okay, what would be affected really is the original previous node of the node that you want to indicate where you're going to add it before. Okay, so what would happen is, okay, Mm, okay, what would happen is like this. Okay, it would remember this is the node that you have specified where you would like to add the new node before. Okay, so the new node would be placed before this node here. So what would happen is this would be pointing here. Okay, then oops, then this would be pointing here. Then what would happen is instead of this pointing to this node, okay, what would happen is it would now point to this node here, and this node here would be pointing to that node. No, this should not be 1200. This should be 1700. Okay, so you get the idea? So there are two scenarios. Okay, so let us first work on, okay, let us delete this. Okay, so let us first work on adding after. Okay, so let's say we want to add after the specified node. It's important that you would specify what node. Now, this would be in the assumption, what if in the case of duplicates? Okay, now, really, what would happen is it would add to the first instance to where that data has been initially found. What would happen really is you are okay, again, you are traversing. Okay, there's a traversal here. Okay, so you are traversing to that node, then you get to decide. Okay, if it's add after and add before. So first is we're going to create the add after. So add after. So there are okay two parameters that you would like to accept for that method. Okay, the position or the x here would be in which node. Okay, you would be referring to the data, di ba? Remember when you are displaying, okay, when you are displaying this, you could only really see the data. So it makes sense that what you would ask as a parameter for that method would be the data. Okay, okay. So this would be the uh, an existing node that you want to point out where you want to add the node after. Then of course the data, okay? The data or the content of the new node or the data of the new node, okay? So n is equal to self.head, okay? What we should first do is we're going to check if uh, that node exists, okay? So how do we know if that node exists? Okay, we know that that node exists if okay we get to stop at a point where we could find that data. Okay, now it is of course possible that that data does not exist, meaning you could not say, let's say you want to add a new node after the node which have a data 20. Okay, now let's say you want to add a new node where you have a data of 70. At this point, there's no node here that holds the data 70. So what would happen is it would continue to traverse that list until it encounters the reference which is none. Okay? Or essentially uh, it arrived at the end of the list without finding the data. Okay, so of course we need first to check if that data exists. So ends of that head, again, this is very similar to what we have done so far when we are traversing. So I'll just write this through. So while n is not equal to none, okay, okay, if n dot data is equal to x, again, this is the x here is the unexisting data in your list. Okay, if what you have specified, okay, while you are traversing, diba? You are going to check. While you are traversing on these nodes, you are actually checking on this data part of our nodes here. If n dot data, remember n here is used to traverse, okay, similar to what we have done. We have been updating the value of n in between the reference, the memory location and the references, diba? So check niya dere, pagtan-an niya diha, wala. Okay? So it moves to the next, it checks the next reference to check if there is, if there's still other nodes in that list. Okay? So check until if, let's say if you have specified 20, so until that is the case, okay, then we need to iterate. Okay? If that is the case, meaning if end that data, the end that data here, okay, remember, the end that data here is not this data here, ha? Okay? The end that data refers to this you while you are traversing. Okay? So when you traverse at this point where end that data at this end is equal to the position where you want the new data. This is the new data. Okay? You want the new data or the new node holding that new data to be placed after. Okay? So if it exists, okay? Let's say you want to put it at 20. So if n dot data is equal to 20, then we have essentially found that item in our node. So we break, okay? So we stop our iteration, we stop on that current value of n, okay? So n is equal to n dot reference. Okay, saan ha? While n is not none, kaya nila, let us, okay, let us revise what I have done. Okay, while n is not equal to none, it will always, okay, it would, okay, this would, diba, it would traverse. Okay, so if it's not equal to none, okay, there are two scenarios. Okay, while it is, while it's until it's none, of course it would end. Okay, so how are we going to do the actual traversion? Okay, n is equal to n dot ref, diba? So while it's none, at this point, it is just traversing until it arrives with at the end of our node. But we want to, okay, we want to stop to the point where what item or what node in our list that has a data of, let's say, 20. Okay, so if there exists. So if there exists, how are we going to do that? So if and that data, okay, as we traverse to these ends here or these nodes here, okay, upon checking if n that data is equal to x, okay, then break, okay. So there are two possible scenarios on which value we will have our n here, okay. If this has been encountered, then the value of our n, okay, the value of the point that we have stopped, okay, in our traversal is at the point where x is equal to the n data upon traversing. But if it so happen, okay, that it could not find, okay, let's say could not find 20. Let's say we have indicated there instead of 20, we have indicated 70. Okay, it is possible that it would not encounter this, but it would definitely stop since we have stated here that as long as n is not equal to none, it gets to perform this. So there are two scenarios, okay, when this is done iterating or when this iteration ends, okay. First is if it find that location that you want to stop or it has traversed, okay, it has traversed in the entirety of the list without finding it. So how do we check if which is the case? Okay, so first is if n is equal to none. Okay, if n is equal to none, meaning if it gets to iterate across, di ba? When we the last value of n here would be this statement, would be determined by this statement here. Okay, the last iteration, okay, this statement of the last iteration, which is n.ref. If it gets to arrive here, di ba? If it gets to arrive here that it has the value of none, okay, di ba? While n is not equal, if n is equal to none, then it would stop. At this point, if that stopped without finding the value of n, we actually have a value of n as none. So that is the reference. Okay, this part here. Okay, so if that is the case, then we could say that print item not in list. Else, the else part here will happen, okay, if this is true. If this is true, okay, let's say n is 20, okay, then we have specified here 20 as a position, okay. If this is true, then break. It would stop iterating, and whatever the value of n here, okay, n then would be stored, okay, that in the or would be used, okay, okay, in this else part here, okay. So then we would have, okay, what we would do, so new node is equal to, so here we are just, at this point, we are creating the new node. Okay, again, of course, if we want to add a new node, we need first to instantiate, okay, an object for that class. Okay, new node dot reference. Okay, so let's say at this point, let's say it has been determined that the location exists and we want to add after that node. So upon creating this, okay, we'll now have, okay, so this, uh, okay, kana. So let's move this. Okay, so new node data. Okay, what is the data? Let's say we would like to SLL dot add, ito, add after. So the parameters for this is, okay, first is what? The location where you want to add it. So let's say I want to add that to the node that has a data of 20. Then what would be the data for that actual node that you're adding? So let's say I'm going to add 60. Okay. So the data for this newly created node, okay, upon creation of this node, so let's say we have here 1,700 as upon creation of this node, okay, there would be a memory location assigned to this object. So arbitrarily, we might say it's 1,700. So as an example, so we have 60, okay, since this is the parameter that we have provided, okay, and this is still none, di ba? Okay, kana. new node dot reference, okay, so this part here, okay, new node dot reference is equal to n dot reference, okay. So what is n dot reference? Remember, n stop here when n dot data is 20. So if n dot data is 20, what is n dot reference? N dot reference is this, 1,300. Okay? So the new node, okay, the reference for that would be equal to n dot reference. Okay? So n dot reference is equal to, come on, 1,300. Okay. So what happened really is you have established a link. Okay. So insert um, illustration shape. Okay. You have established this link here. As you can see, it's still missing something. You want to establish the link from this. Instead of pointing here, you want to point this to here. So what should we do? Okay. Again, what is this part here? That is, since this is n dot data, this is n dot ref. So what we're going to do is we're going to write n dot ref is equal to what? This memory location of the newly created node, which is our new node. And that's it. Okay. So instead of, okay, so upon doing this, n dot ref would be equal to the memory location for this newly created node, which is 1,700 supposedly in this case. So it's now pointing to, okay, so it's now pointing to this. Okay, so that's it. So now you have this node as our head, second, third, fourth, fifth, and sixth. Okay, so we have 6 nodes in that order. So what we could see now is, okay, you would now see, okay, 40, 10, 20, 60, 30, and 50. If you're going to run this, 60 has been, okay, situated after 20, which is the same as this structure here. 40, 10, 20, 60, 30, and 50. Okay, so how about, okay, diba? We could add after. And how about adding before? Okay, so add before. Oops. So we would accept similar parameters. So we would write the location that we would add and the data, the actual data for that node that we are adding. So let's say SLL that add, let's say before, let's use 20. Okay, let's use 20. Then let's say we're going to add 70. Okay, so what we would like to do is, okay, a new node would be created here. So which would be, so pointing here, then pointing there. Okay, so let's say this is 1,800. Then let's say the data is 70. Then of course this should now be pointing. So this should now be pointing to the, remember this is the previous node of the node that you have indicated. Okay, so this would actually be the node that would be affected alongside with this new node here. Okay, so it should be 1,800, then here would be 1,200. Okay, so we would like that to happen. If we want, if we indicate 20 here. Okay, so let's first create, okay, the code for that. So add before. Now, again, there are a few things you need to consider. Okay, so if you're adding on an empty list, okay, let's say it should not add. Okay, let's say you could only add. Okay, di ba? You cannot really, if you're adding in an empty list, technically there is no node that you could refer to. Okay, so imagine these are all non-existent. Okay, what it would only have if a list is empty. Remember how it would appear. Okay, it would appear like this. Okay, diba? Again, a singly linked list could exist. Okay, as a structure which has no nodes in it. So this is valid. But we could not really perform this operation, okay, add before, okay, add before if it's empty, okay? Since we could not, diba? How could we could not specify. Again, this is just a pointer. This is not a node, okay? This is just a pointer to a node where it should start, which serve as the head. So if it's empty, if self dot head is equal to none, meaning it's empty, you're going to print, okay? Could not really do that. Uh, could not add, or just say list is empty. List is empty. You say cannot be, cannot be, list is empty. Okay, let's say then return. Again, writing a return would essentially, okay, return that function, meaning it gets to finish execution of that function. It would not, it's like a break statement for loops, but in this case, it's we're using functions, so we're going to use return to preemptively move outside that execution of our function. Okay. Now, another scenario is, let's say what you have specified is your head. Okay, let's say you want to add before the head. Okay, so you want to add before 40. So if that is the case, then it's similar to as if you are adding at the beginning, diba? So with that, you can just simply copy that, okay? So if x is equal to self, diba? How would we know if the data that it is referring to is the head? Remember, this is our head, okay? This is our head.ref, but we are concerned with the data. So we are going to write head.data or self.head.data. Okay, so if this head.data, okay, is equal to the uh, is 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 the value of the data that you would like where to add your node before, you are essentially just adding that, di ba? It's similar to adding it at the beginning. That's why we would simply copy, okay? I'm going to copy this, okay? And now, then return, okay? So if it's empty, cannot do that. If the if it exists, but it exists at the start or it exists as the head of our linked list, then it would just simply perform as if you are adding at the beginning of that list. Okay. Now, if it's not the case, meaning it's just before the node that you've specified and there is still a previous node, so nga ni. Okay? Okay, again, we traverse. Okay, again, this is very similar, familiar, and that ref, okay, is not equal to none. Okay, so if n dot ref dot data is equal to x. Actually, it's the same with what you have done earlier. Okay, similar, not really the same. It's similar. Okay, similar to this, but we are actually, okay. If you've noticed, okay, why are we using n.ref.data, not n.data? Ah, ano yun? Okay. If we are adding before, okay, you would like to check. Okay, you would actually you remember what I have mentioned earlier. The node that is affected really is the previous node. Okay, so what happened is yung ano. Okay, so let's do this. Okay, n is equal to self that head, so it's pointing here. While n dot ref is equal to none, so the reference here is it's still not none. So this is okay. This is the case. So if what is n dot ref dot data? Okay. At this iteration, this is n. Okay. This is n. This is n dot data. Okay. This is n dot ref. N dot ref. Okay. Diba? This is n dot ref. N dot ref dot data. Really, this is viewing. Okay. This is viewing the data of the next node. Did you notice the how it is done or how it's supposed to do? Okay, and that ref points to here. So and that ref that data points to here. So really, you want to stop iterating if the data of your next reference is the data that you're pointing that you want uh, to add before. So if you're working with let's uh we are using 20, di ba? So kani. And that self that head. Okay, so this is here. While and that ref, okay, and that ref is not none. Okay, so you traverse. It's going to check is n that ref here that data is equal to the data of the node that we want to add before to, okay, we would like to stop. Okay, so at this point, n.ref.data is, so man, it's 10. It's not 20. Okay. So if you continue this, diba, we want to stop to the point where we get to check that the n.ref.data is equal to the node that we are, if we want to add before. Okay. So of course we need to n is equals to n.ref. Diba? You're familiar with this. You're familiar with this part here. Okay? Kani and kani. Okay? It's just iterating across this. But the breaking condition depends on the data of the reference. Okay? So, and if we go back, okay, to the first iteration, and that ref that data is 10. Okay? Since it's not equal to x, and as long as it's none, again, it's similar to what we have demonstrated earlier. There are two scenarios. Okay? It could be that this gets to iterate the entire list without finding x, or it gets to find it. Okay? So how it gets to find is kani. So the first iteration, and that ref that data is 10. Now, since that is not the case, okay, it would reassign the value of n to n dot ref. So n dot ref is, okay, 1100. Remember, it's just checking the breaking condition here, but currently in the iteration, it's still here. Okay, so n is equal to n dot ref. So at this point, okay, it is now pointing to this point here. Now, n dot ref is not none, so it gets to perform this. So n dot ref, that is 1200. So here, so that data is this. If that is equal to the node where you want to put your node before, then break. Since that is the case, n dot ref dot data, okay, when n is here, n dot ref dot data is 20, okay, so it would stop, it would break. So with that, we are going to, okay, put the node. At first, okay, again, di ba? Two scenarios. If n dot ref is none, meaning it gets similar to what we have done here. Okay, if it traversed fully to the list without encountering this, then essentially you have arrived to the end of our list. So n dot ref is equal to none. So print uh, item not in list. Else, if this was the case, or if this happens along the iterating, while iteration, okay, or while looping, okay, so it would break. So now we end with this value of n here. So what we can do is, okay, new node is equal to node data. So again, similar, we are just adding, okay? We're just creating a new node, okay? So let's say we want to add here. So let's create a new node here, okay? So let's say this is 1800, okay? Upon creation of that object, it has a memory location of 1800. Then we have the data, which is, what was the data? 70, okay? So 70. And initially, that would be none. So what we want is, okay, what we want, okay? So new node dot reference, okay? New node dot reference is equal to, where should we be pointing? Okay, we are going to use this value of uh, n dot ref as our reference here, so that it would point to here. So kibale, we would like to add 1200 here, so that, okay, this new node would point to the node before we have specified, which is 20. So that is new node dot ref is equal to n dot ref. So dire niya nagikuha. So initially that is none, but it retrieved the value of the, diba? We want to to add that before. It makes sense that the value of our 1200, the value here would be this node here. Okay? So we're going to delete that, okay? But we still need to link this here. So what we're going to do is n dot ref, okay? The new value of this reference here is saman, new node. So now we have, okay, 1,800 here, okay? Okay, so now with this, we now have a list which comprises of element of nodes which have data 40, 10, 70, 20, 60, 30, and 50. So if we're going to run this, okay, we have added that, we have called that. Okay, so there's an error. There should be, okay, column. So as you get to see here, so 40, 10, 70, 20, 60, 30, and 50. Okay, so siguro I'll end the first part here. Next part would I would be discussing how to add if your list is empty. Okay, so and also the deletion. Okay, so that's it. Actually, it's yeah. Let's just continue on with the next part since my the headset that I'm using is its battery is getting low. Okay, so see you next video or next part of this discussion.